Start. Okay. Yeah, so I already wrote a few things down. I realized that I forgot to mention some important facts about omega-freeness, namely that every Hardy field actually can be extended to an omega-free Hardy field. And that's actually not so easy. Took us considerable effort. But in fact, it's actually by now 4 or 5 years old. But it's an important step towards later things. And then I also want to highlight the fact that I defined omega-freeness basically in terms of pseudo-Cauchy sequences having no pseudo limit in the certain kinds of pseudo-Cauchy sequences having no pseudo limit in the field. But I mean, if you trace everything back in the correct way, you can also see that it's equivalent to a first order condition, namely of a given by a universal existential sentence, namely K satisfies for all f that exists in G, so that G strictly dominates 1, and f minus omega G double dagger, yeah, the dagger of the dagger, dominates the square of G dagger. Remember, omega is defined for any differential field by minus 2Z prime minus Z squared. So this is a pretty complicated expression, but it is first order. And
yes. May I interrupt by a question? Jean-Philippe Rollin. Is it also true that every H field with asymptotic integration extends to an omega-free H field with asymptotic integration? Ah, okay.
Yeah. Basically, that is much easier.
Ah, okay. Okay. Yeah. Thank you.
And that's in our book.
Okay.
But that is not. That was found later.
Okay.
I can say a bit more on this first point, namely, it actually Hardy field extends to differentially algebraic Hardy field extension, right? So differentially algebraic meaning that in every element in the extension satisfies a non-trivial differential equation, algebraic differential equation over the one you start, the smaller one. Right. Here on the second point, this is not just true for Hardy fields, but for arbitrary H fields with asymptotic integration, right? Right. And I mean, you see, this is because of the form of this sentence. This is also, you see that omega-free is an inductive property. If you take an increasing sequence of omega-free H fields, then the union is also of omega-free H fields, then the union is also omega-free. So, and so, for example, going back to the first part, every Hardy field extends to an omega-free Hardy field. Well, that can be combined with Liouville closed, right? Every Hardy field extends to a Liouville closed omega-free Hardy field, because you can keep extending and alternating, going to an omega-free extension, then to a Liouville closed extension, omega-free extension, Liouville closed, and take the union, and you get things that are both omega-free and Liouville closed. So, I mean, these are routine remarks, but I thought I should make them. Yeah, so now I actually would like to explain a much stronger property. Omega-3 is already very well behaved, but there is something called Newtonianity, which is in some sense even more crucial. But it's a little bit, it takes a bit of work to explain that. And before I do that, I want to describe roughly the program that I'm going to follow after, for the rest of the course. I understand my course is actually ending early April 7 or something like that, right?
It's with U of T. I don't know when U of T course is in.
Oh, yeah, but I read somewhere that it was the ending in April 7 or so. Oh, okay, yeah. Anyway, I'll check. But I will have time I wrote down a program that I think I can carry out in the time left. And the first thing the first main thing is to give a rough sketch, very rough sketch actually. I'll tell you why, of our main theorem. I mean, about Hardy fields. Hardy fields. And well, basically, the proof was finished end of 2020. And it's the following: all maximal Hardy fields. I mean, I mentioned this in my workshop lectures. All maximal Hardy fields are well, Liouville closed, of course, because but also omega-3 and Newtonian are Liouville closed, are Liouville closed, omega-3 and Newtonian, and right. And therefore, because of the results in our book, we already know that these axioms, together with small derivation, completely axiomatized the theory of the differential field of Transseries, right? And so let's say, therefore, by our book, by the results in our book, all are elementarily equivalent as ordered differential fields to the differential field of Transseries, because that also has these properties, and we know, and its derivation is small. Yeah, derivative of an infinitesimal is infinitesimal, and we know that these completely determine the elementary theory, which is also model complete, and so on. Yeah, what did I want to say here? Yeah, actually, this is a rather weak, rather special version of the main theorem, because what we really prove is that all D-maximal Hardy fields have these properties. Now, D-maximal means it has no differentially algebraic Hardy field extensions at all. Of course, a maximal Hardy field has no Hardy field extension at all except itself, but D-maximal is more general, namely there are no differentially algebraic Hardy field extensions except itself. And of course, D-maximal Hardy fields can be very small compared to maximal Hardy field. The maximum, yeah. Another thing I want to say, just to give you an impression, T, the differential field of Transseries, it looks like a very big differential field, but it's absolutely tiny compared to maximal Hardy fields. These maximal Hardy fields are, once you start looking at them, turn out to be gigantic compared to T. I'll say more about that because the second thing that I want to, so a rough sketch, I'll say why, because the full proof is like 150 pages, and I can't do that here. But but I'm going to use this as a black box. Use this result to prove in some detail, modulo the black box, so to say, a key part of, again, of the second main fact that we proved, and that was the proof of that was only finished last August. For any Hardy fields, it's sort of a complement to the first one. Any Hardy field H and countable subsets A less than B, right? That means every element in capital A is less than every element in capital B. You can always find an element in between in the bigger Hardy field or in the same Hardy field. It exists Y in a Hardy field extension such that A less than Y less than B. You might recognize, so in particular, if you are in a maximal Hardy field and you have countable subsets A less than B there, then you will be able to find this Y in that in the same maximal Hardy field, because there aren't any extensions except itself. And that means that the underlying ordered set of a maximal Hardy field is eta 1 in the sense of Hausdorff, right? And that has eta 1, well, that is if you have an ordered set, linearly ordered set, and you have countable subsets A less than B, there is always a Y in between. And that is, for example, for real closed field, that's the same as all-of-one saturated. Now, of course, maximal Hardy fields cannot be all-of-one saturated because the field of constants is just the reals, which is not, this is not even one saturated. But one can still use this fact to show that assuming the continuum hypothesis, all maximal Hardy fields are isomorphic. Yeah, and of course you have to keep in mind there are very many maximal Hardy fields. That's another fact that we proved in the a while ago, that there are 2 to the continuum many maximal Hardy fields, which is sort of the maximum what it could possibly be. And now I want to make some kind of informal remarks on the state of the write-up of these things. Yeah, so I already mentioned we basically finished the proof of that end of 2020, and this last August. But yeah, so it's all fully written up, both things. But the proof of this thing is really long and complicated. about 150 pages. And even worse, we have written notes that are 350 pages. And the reason for that is that we include a lot of classical material with full proofs. Like we need certain facts about, there is a classical theory of almost periodic functions. And there is also classical material on uniform distribution modulo 1. And it turns out we actually need results from these classical subjects. And we, just to learn the stuff ourselves in a thorough way, we wrote everything out. And so that of course adds to the length of the notes. And also a lot about linear differential equations and self-adjoint operators and all that. So there is a lot more material in these notes than what is needed for this. And we also developed some topics further to answer questions posed by Bojanitsan and simply questions that arise in our own thinking. And I would be happy to put these notes on the archive. I think they are not in perfect shape, but in good enough shape for other people to read. But the problem is that my co-authors don't agree with that. Co-authors meaning Matthias Aschenbrenner and Joris van der Hoeven, because Joris still has to read those notes. And this is, but he will be here, and then he will have, I think, in May, and then he will have time to focus on it. For this result, that is also, well, it's certainly not trivial, but certainly a lot less. We have a full paper there, 50 pages. But it has not been read yet by Matthias, and so that's another reason that I'm not allowed to put it on the archive. So I hope that this all will happen in this summer, but that will be after after this semester, right? Okay, so today I just want to do some preliminary stuff so that on Thursday I can really talk about Newtonianity, or, well, with a little bit of luck. So some preliminaries, yeah. I mean, I'm sure that many of you already are quite familiar with this, but for those who are not, I want to say a few things about differential polynomials. Because Newtonianity simply means that certain kinds of differential polynomials will have zeros. Polynomials. Yeah, so let R be a different, yeah, I did define early on in the course, I think, that R be a differential ring, yeah. Remember, this includes the assumption that it contains all the rational, it contains Q, the field of rational numbers, as a subring, and then it has a derivation. Yeah, R be a differential ring, and then yeah, and let me define, yeah, with derivation. Let me denote the derivation by by this delta, but of course I will also simply write y prime for the derivative of an element y, and y double prime for the delta square y. Okay, and then the diff. Okay. Okay, R. Yeah. So this is the standard notation for the ring of differential polynomials in one indeterminate y. And what is it? Well, as a ring, it is simply the polynomial ring in infinitely many variables. Yeah, so for every r, natural number r, you have a variable y superscript r. And of course, when r is 0, this is just y, and this is y. Y1 is this, etc. And of course, you have to understand this correctly. In every differential polynomial, that means every element in this polynomial ring, only finitely many of those y superscript r can actually occur. And so, yeah, but this is not just a ring extension of R. It's a differential ring extension. Yeah? Ry is a differential ring extension of R, and that means the derivation is extended on R. And how do we extend the derivation in such a way that the derivative of yr is yr plus 1? Yeah, is a differential ring with, in other words, derivative. Yeah, I always indicate the derivation this way unless it would. So I use the same letter here. The delta of yr equals yr plus 1. And that completely determines the extended derivation on this differential polynomial ring. And okay. Now the important thing, of course, just like with ordinary polynomials, is that you can evaluate them at elements of R, but actually one wants to evaluate them also at elements of any differential ring extension of R. So for each for any differential ring S containing R, that means this indicates that it extends that that is a ring extension of R, and that the derivation of S extends the derivation of S extends the derivation of R. For any and y in S, we can substitute. Y, yeah, for the indeterminate, the indifferential indeterminate y in in a differential polynomial py in Ry. And how do we do that? Yeah, write py as an ordinary polynomial in the. It's a differential polynomial in just one indeterminate, but when you write it as an ordinary polynomial, it becomes y prime, y double prime, etc. Becomes a polynomial in all these indeterminates, and then py is, well, just what you think. You plug in little y for big Y, and then little y prime for big Y prime, Y double prime, etc. Just the obvious thing to do. But then the important thing here is that this substitution or evaluation at little y is gives you a differential ring homomorphism. Yeah, this gives a differential ring morphism. Where so py goes to p little y from the polynomial ring into S, right? The value here, this is an element of S. Yeah, so I mean, just what you are used to for ordinary polynomials and evaluating them at a certain element. Right. Yeah, and another remark I want to make. Sometimes we want to consider the differential ring generated by little y over R. Yeah? So this is differential ring generated by little y over R in S, if you like to add that. Yeah, it's the smallest differential ring, subring of S that contains R and also little y. And of course, it is simply the set of all the value, all the PYs. P in R capital Y. Yeah. Right. And so, in some sense, you can see that that then writing P as P capital Y makes sense because it is actually the value of capital P when you substitute. If you take for R, S, R, this differential polynomial ring, and you take for little y, big Y, then then P, yeah, we often, this justifies writing P as PY because it's just the value of P at big Y. Anyway, these are kind of trivialities, but nevertheless, they have to be mentioned once, and then just work with them. Yeah. Just like ordinary polynomials, you can, an ordinary polynomial is simply the sum of its homogeneous parts of various degrees, right? PD is homogeneous. So if you only take the part, the terms in capital P that are of degree, are of fixed degree D, then you get PD is the homogeneous parts of degree D. Oh, I forgot to say, the important thing about that I have to add is what is the order of a differential polynomial? Yeah. Okay, let me see. For a non-zero, for capital P in Ry, which is not zero, the order is simply the smallest r such that the order of P is the least natural number such that capital P is y prime up to yr. Right. So in particular, the order of p being 0 simply means that it is an ordinary polynomial in capital Y, and there are no higher derivatives occurring at all.
Do you mean degree or order?
Here I mean degree, yes. I should have, that's why I went back to this blackboard, not to get confused with the degree. Yeah, no, the degree is a different thing.
Just in Y, just in the variable Y.
Oh, no, yeah, part of degree D and Y. Thanks. Yeah, of course, every term in this polynomial is of the form an element of R multiplied by Y to some power times Y prime to some power, etc. And so you have to add, you have to look at the total degree of those, of that you get, right? Yeah, and what is particularly important is the P sub 1, the linear part, or the degree 1 part, I should say, because the linear part actually will have a different meaning. In particular, yeah, P1. So P1 is simply the homogeneous part of degree 1. So that looks like this. Summation AI, YI, where every variable for I is 0 up to R, if R is an upper bound for the order, of P, yeah, P1, yeah. Of course, the coefficients here are in R. Right. Okay, so that is what I wanted to say for now on differential polynomials, and we will come back to it. But next, I want to say something about linear differential operators, which are, yeah, let me see. Maybe I should. Linear differential operators. And there is a sort of subtle difference between linear differential operators and differential polynomials of degree 1, homogeneous. And I have to keep that in. Okay, so again, R is, as before, is a differential ring. And then what is the ring? The ring R. Okay, yeah. We take this symbol for the derivation, and then we sort of build a ring out of it. The ring R delta, the ring of differential of linear differential operators over R. Well, first of all, it's a ring extension. It's extension of R. It contains R as a subring. But in general, this will not be commutative. R, in my definition of a differential ring, we assume commutativity. And of course, the polynomial rings are also, these differential polynomial rings are also commutative, but in general, not commutative, as we will see, as we will because I haven't defined the multiplication or addition yet, and they are not commutative, as we will see. And here is the formal description. It is as an R, as a left R module, it's just a free, it as a left R module. It is free with basis, well, the powers of delta, but for the moment, these powers are simply computed as delta with basis delta 0, delta 1, delta 2, etc. For now, just symbols. For now, just symbols. In other words, for every natural number n you have, or r, you have a delta to the symbol delta to the r, and you take these symbols as a basis for a free R module. Yeah, so, in other words, R is simply the direct sum, R delta is direct sum R delta to the power n. Right, and the identity of the ring is delta to the 0, yeah. Okay. Comma, with ring identity, the identity, the multiplicative identity of this ring, identity of R delta is delta to the power 0. And of course, we will just write 1, yeah, also written as 1. And you can, of course, you can just identify it therefore with the element, with the identity of the ring R itself, right? Which we also typically denote by 1. And the multiplication of these basis elements and multiplication, well, I have to tell you how to multiply two such powers, or I shouldn't say powers. They will turn out to be powers, but multiplication given by just what you think. Delta m multiplied by delta to n is delta to the power m plus n. And you also have to say, well, multiplication on the left by an element of R is simply, you know, you don't have to explain that. We already said it's a left R module on this basis. But how do you multiply a delta with an element of R on the right? So you have to say what you mean by delta A. Yeah, delta A equals A delta, so plus A prime for A and R. So, oh, and delta here stands for delta to the power 1. Yeah, A and R with delta used as abbreviation for delta to the power 1, not to be confused with the derivation delta of the ring R. This is a subtle point, but for the moment, I should formally write delta 1A is A delta 1 plus A prime. A prime here is, what is A prime? This is simply the derivative of A with respect to the derivation delta on R. But you say it's more intuitive to write it this way without the Yeah. So delta to the power 1 will simply be written as delta, but not to be confused with the derivation delta on R. Why not? Why shouldn't we confuse it with? Because if the derivation is trivial, delta is 0. That doesn't mean that delta to the that this delta is this delta to the power 1 is 0. Delta 1 is simply one of the basis elements of this module. Right. Okay. I hope this is not. Okay. These rules completely determine the multiplication on the. If these rules, you completely the multiplication on this of this ring is completely determined, and of course one has to check that everything. That is really a ring and so on. And you see from this rule that it's not necessarily commutative. It will be commutative if A prime is 0 for every element A and R. And that's the only, and then it will just, and in that case, this will just look like a polynomial ring in the variable delta over R, right? Right. But that's, of course, an exceptional case. Usually the derivation delta is not trivial, and then A prime here will, for some A's at least, will not be 0. And so, right. Okay. Aha. Yeah, so how do these linear differential operators then yeah. Okay. So they look like this, right? A linear differential operator, an element in this ring, is simply a linear combination of these symbols delta to the power I. Okay. By the way, since delta is just an abbreviation for delta to the power 1, this becomes then, because of this rule, this means that delta to the power n is simply the nth power of delta, right? So so the notation is correct. I mean, it really is the nth power of delta when delta is viewed as delta 1 here. Right. So summation AI delta I, that's how these linear differential operators look like, and we also define the order of order, just like for the differential polynomial is R if AR is not 0. Yeah, here again, the coefficient AI I assuming to be from capital R. And now these linear differential operators really do define operators. An operator, so I'll call them an operator A. Yeah, I'm typically using capital letters for these operators. I delta to power I and R delta defines for each differential ring extension, for each differential ring S containing R, a CS linear map, or namely it sends Y to summation AI, and then you just apply, you interpret delta to the I as the I derivative of. Oh yeah, what is CS? If you have a differential ring S, then C sub S is the ring of constants. the subring of constants, which means the constants are simply the elements whose derivative is 0. Right, and you can easily check that this is a linear map when you view S as a module over C sub S. Yeah, and the point is now that the reason for defining the multiplication that way is exactly that composition of such linear maps corresponds exactly to multiplication of the operators. So yeah, okay. So no, yeah. Let me first say, in the case that A is simply for A is delta to the power 1. This is just the derivation on S. This is just y goes to y prime goes to S. And of course, for A is 1. This would be the identity map. And for A is an element of, if A happens to be just an element of R, this is multiplication by R. And this is y goes to AY. A by, if you have two operators, A and capital B, and then this is simply AB y. Yeah? So in other words, multiplying operators now corresponds to composing the corresponding linear maps. Okay, well, let me see. Right. Yeah, so of course there is a resemblance. Yeah, this resembles this linear differential or this polynomial does the same thing, so to say, as this linear differential operator. Right? Because if you evaluate this at an element little y in a differential ring extension S, you get the same thing. But nevertheless, you shouldn't confuse them. I mean, multiplying differential polynomials is commutative, and in fact, if you multiply two of them like that, then it's not even of degree 1 anymore. It's of degree 2. But here you stay in degree, well, composing is you stay within the ring of differential operators. So and it's right. Okay. Yeah, okay, so now I want to I guess I should I want to say something more specific about the case where our differential ring is a differential field, because then it turns out that this ring of differential operators has very nice algebraic properties, which are highly useful. So now, from now on, a differential field, just a differential ring which happens to be a field, and of course we are assuming it contains Q, so it's of characteristic 0, just to avoid certain exceptional behavior. Okay, then K delta has excellent algebraic properties, and I want to mention a few, despite being not commutative. Yeah, one of the key ones is that you have Euclidean division with remainder, right? Just as for ordinary polynomials, you over a field, you Euclidean division with remainder. What do I mean? For A, B, K delta, and B not zero, there are unique QR also in K delta, such that A is Q times B plus R, and where the order of R will be smaller than the order of B. Yeah? The order of R less than the order of B. Yeah, you might, of course, I should also say that the order of zeros is minus infinity. Otherwise, I only define the order. Did I define the order somewhere? Oh yeah, right. The order of this thing is R if AR is not zero. So and the order of zero is minus infinity. So this makes always sense, right? I mean, if the order of B happens to be zero, which means B happens to be just a non-zero element of the ring R, then that means that this has to be, this capital R here has to be zero. Oh, of course, this is a little bad. The notation is not, it's unfortunate perhaps, because this R has nothing to do with the ring R that I was working with earlier, but I hope that's clear. The thing is, this is only a right division or left, whatever it is. It's one, there is also Euclidean division where the Q happens, where you have the Q here, right? So you have two Euclidean divisions with remainder. One where the quotient Q is on the left, and there is also one where it happens to be on the right. You can simply, in fact, there is a kind of duality which I'm not going to state, I think, where any result that you have for where the non-commutativity plays a role, you can sort of reverse the order of the factors. But okay, I'm not going to say that now. Yeah, so there are right. If you consider this as a left version of Euclidean division, the remainder is also a right version. Right, this has as an just as for ordinary polynomials in one variable over a field, this has the consequence that every left. Well, here it will say that every left ideal is generated by one element. Therefore, yeah, one can use that. Yeah, in the usual way, every left ideal in K delta is of the form delta multiply. Yeah, all the left multiples of one particular operator, and likewise every right ideal is of the form A times K delta. In other words, all the right multiples of a fixed operator. Okay, let me. Oh wait, I'm already over time. Sorry, someone should have told me. Is that a seminar?
Yes.
Okay, so then I better stop. Yeah.
Thank you.
Okay. Yeah. Yeah, not much news today, but need to go through these motions too. Hmm?
Just have a good intuition why we have